Hello everyone, I'm Akash and in today's video we will solve an interesting question on real analysis from TIFR 2016 exam. Question is, which of the following is false? As we can see here from options, we need to verify the convergence and divergence of given series. So let's verify one by one. We will use limit comparison test as well as the necessary condition for the convergence of series. So let us first recall what is limit comparison test. If series un and series vn are series of positive real numbers and limit n tends to infinity, un over vn is equals to L, finite and non-zero, okay, then series un and series vn are converges or diverges together. Okay, we will use this limit comparison test. Okay, so this test states that if un and vn are series of positive real numbers and if this limit exists and is finite and non-zero, then both the series are convergent or both the series are divergent. So let's use this test to verify option A. Option A is series sine of 1 upon n diverges. So let take un be series sine of 1 upon n, okay, and let take vn be series 1 over n, okay. We know this is a harmonic series, and as we have seen in our previous video that this series is a divergent and it diverges to plus infinity. Now let's compute this limit. Limit n tends to infinity sine of 1 upon n upon 1 upon n, okay. Now as n tends to infinity, 1 upon n goes to 0. So if I substitute x equals to 1 upon n, then as n tends to infinity, x goes to 0. So this limit is nothing but equals to limit x tends to 0 sine of x upon x. I have just substituted x equals to 1 upon n. Okay. So both the limits are equal and we know this limit is equals to 1. And clearly this is finite and non-zero. So according to the limit comparison test, these both series converges or diverges together. But we know that this harmonic series is divergent and it diverges to plus infinity. So this implies series sine of 1 over n is divergent, that is diverges. So statement in option A is a true statement, but we have to select the false one. So this option is incorrect because we have to select the false statement, but statement in option A is a true statement. So we discarded it. Now let's verify the statement in option B, which is summation sine of 1 upon n square converges. We will use same limit comparison test. Now this time we will consider un as sine of 1 upon n square and vn as series 1 upon n square. And we know by p series test that series 1 over n to the power p is convergent if p greater than 1. So by this p series test, this series as p equals to 2 here, which is greater than 1, this series 1 upon n square is convergent series. Now let's first compute the limit. Limit n tends to infinity un is sine of 1 upon n square and vn is 1 upon n square. Again, as n tends to infinity, 1 upon n square goes to 0. So if I substitute x equals to 1 upon n square, then x goes to 0. So this limit is nothing but equals to this limit, and this limit is 1, which is non-zero and finite. So by limit comparison test, this both series converges or diverges together. But series 1 upon n square is convergent by p series test. So this implies series sine of 1 upon n square is convergent. Okay. So the statement in a B is also true statement, but we have to select the false one. So this option B is also discarded. Okay. Now let's verify option C. We will use the necessary condition for the convergence of series. What is necessary condition for the convergence of series? Series AN is convergent, then we must have limit n tends to infinity an equals to 0. This is a necessary condition for the convergence of series. If this series is convergent, then we must have limit n tends to infinity an equals to 0. If this limit is not equals to 0, then this series cannot be a convergent series. Okay. If this limit not equals to 0, then this series cannot be a convergent series. Now, let's consider this limit for this. Limit n tends to infinity cos of 1 upon n. Here n is cos of 1 upon n. As n tends to infinity, 1 upon n goes to 0. So this is nothing but cos 0, and cos 0 is 1, which is non-zero. So as this limit is not equals to 0, so this series cannot be a convergent. So as this limit not equals to 0, so this series cannot be a convergent series. But it is a series of positive real numbers, so it must be a divergent series. Okay, because it is not a convergent series and it is a series of positive real numbers, so it must be a divergent series. So statement in option C is also a true statement, but we have to select the false one. So option C is also discarded. So what is remain is option D, which is a correct option, which is the answer to this question. Now let's verify this. Again, we will use necessary condition for the convergence of series. If this series is convergent, then we must have this limit equals to 0. If this limit not equals to 0, then this series cannot be a convergent. So let's consider this limit n tends to infinity an, that is limit n tends to infinity cos of 1 upon n square. Now as n tends to infinity, 1 upon n square goes to 0. So cos of 0, which is 1, not equals to 0. So this limit not equals to 0, then this series cannot be a convergent. So this limit not equals to 0, so this series cannot be a convergent series. But it is given that it is a convergent series. So this statement is a false statement, and we have to select the false one. So the option D is correct. Okay. So the answer is option D. If you found this video interesting and helpful, then please like and share this video and subscribe to our YouTube channel. Thank you for watching.